example, we are having one RAG agent that has access to a knowledge base via a retrieval augmented generation. And this agent is able to connect to an RDS vector database where embeddings of PDFs are stored. So as soon as you upload some data to S3, it will generate embeddings, and those embeddings will then store into the vector database. And the RAG agent can then work with this data here. The second agent is the tools agent, and this agent is able to call Lambda action group. And the Lambda action group is then in turn responsible for communicating with an external API. We also have tracing implemented, so we can track the costs, we can do evaluations, and we can also debug user prompts in production. The application itself consists of authentication and an application service that is deployed to AWS ECS. So let's look into the specific components. So first, let's start with the infrastructure as code. So when you follow the README and you CDK deploy, what is happening under the hood is that those 4 stacks are deployed. So the simplest stack is the authentication. It's just generating a user pool where you can use username password authentication to securely access the app. And you can just create those users in the AWS console after the stack is deployed. The second is the vector stack. It depends on the generative AI CDK constructs that is published by CDK Labs. And it uses this Amazon Aurora vector store. And this vector store, here we use in the most simplest configuration. It already creates an RDS database. And under the hood, it installs PG vector with a custom resource, so that then you can use this vector store as a knowledge base for your data. And that also needs a small VPC, just an isolated subnet to be deployed into. The third stack is the Bedrock stack. So this stack creates a bucket where we deploy our protocols into. The protocols are here in the data folder. At the moment, we only have one protocol, and that's just a medical protocol with 135 pages. So there's a lot in it, and the RAG agent has the responsibility to find out which portions of this PDF are required from the prompt that the user is giving. So here, this knowledge base gets created, and in this case, we are using the Titan embeddings from AWS. We could also use Cohere embeddings from external foundation model. We are having a length of 512 here. That's usually sufficient and reduces costs. We are defining the source. So this is basically the pairing between the knowledge base and the RAG bucket. So we are saying this bucket gets linked to this knowledge base, and also we use a parsing model to parse the PDFs. In this case, we are using Claude 3.5 Sonnet version 1. And we also define a chunking strategy. In that case, we are using a hierarchical chunking with default values for Titan, but there can also be semantic chunking or custom chunking definition. We are deploying a Lambda function so that whenever a PDF gets uploaded to this bucket, it will automatically trigger a refresh of the knowledge base so that we don't have to do that manually. And this function is defined here in the data sync TypeScript. So it just calls the Bedrock agent API, and it starts an ingestion job with the knowledge base ID and the data source ID. So that's done for us. And then we have this deployment where CDK is automatically uploading the PDF files for us from this folder. So that's the RAG part. And now we're talking about the tools function. So for the tools, as I already said, it's deployed to AWS Lambda. So we're having some code that is here in this repository, and it's deployed as a Lambda function. And then we create an action group for Bedrock out of this Lambda function. The action group next to the code always needs to have an open API schema, so the agent knows what actions it can do and what parameters it's feeding to the function and what results is it expecting. So here we can link that JSON schema, and we will see later how it's generated. There is also a role that's allowing the agent to do stuff, and we are overriding some of the prompts. So there is a prompt folder here, and you see that some of the default prompts are overridden. So for example, here in that case, the clinical trial agent, which is the protocol agent, it has certain instructions. So here it says, okay, you're specialized in medical protocols. There's some addition. So if a table is present, always use concrete values. And here's, for example, a definition for the knowledge base and for the orchestration. So those are the things that we needed to modify because the default values were not good enough. You can always provide your own custom instructions. The knowledge base also has instructions, and then we define the protocol agent. We use Claude 3.5 Sonnet version 1, and we override the prompts, and we link it to the knowledge base, and we link it to the user input instructions like that, which are indeed then read from the file here. So there is also the supervisor, and the supervisor we need to create via custom resources, because at the moment CloudFormation does not support the creation of agent collaborations. So here we need to use the AWS SDK, and we are calling it with onCreate, onUpdate, and onDelete definitions. And then we are working with this agent ID for the supervisor, and we are giving it code interpreter capabilities. So the supervisor is then able to execute code on our behalf. And also we are associating two sub-agents to it. So one is the trial agent that gets associated also over a custom resource, and the second one is the protocol agent that gets also associated with this Bedrock associate agent command from the AWS SDK, because there is no CloudFormation support for it yet. And so AWS CDK can also not directly provision it. Then we are preparing the supervisor agent, which is always necessary before you can actually use it, also over a custom resource. And then we are creating an alias, which is like a reference to this deployed version of the agent that we can then use to invoke the agent. So there's a lot happening here in the Bedrock class. That's one of the magic sources that is defined in this blueprint, and you can add your other tools and your other knowledge bases and everything you need to have in this file as well. So much for the infrastructure. Let's look into the source code. First, let's look into the tools that we define. And as I said, here is this open API schema that is defined for us. And we can look what functions are defined here. And those are then the functions that the agent can use. So it looks in the schema and understands, okay, those parameters are available and I'm expecting those responses. And so we are having a function to search trials from clinicaltrials.gov, to get trial details for a specific trial, find the closest trial based on a specific country and zip code and city, and getting inclusion and exclusion criteria. So those are just samples for you to understand how this functionality could be adapted towards your own use case. And what you can see here is that we are using AWS Lambda Power tools. and it will allow us to generate this open API schema automatically. So here in the main, there is only get open API JSON schema, and whenever something has changed here, you just need to run it as a debug configuration, and then it will refresh the schema JSON for you. In order to do that, you need to annotate your function. So you need to specify the types for the parameters, and you need to describe it. And the same goes to the responses. So in this case, we are returning a list of minimal clinical trials, which is defined here in the models, and we're using Pydantic and typing libraries to define all those schemas, and then the OpenAPI generator knows how to generate the schema JSON for us. That's mainly it. You can look into the details of how this is implemented, but it's not super important for the moment. And lastly, we are looking at the Streamlit app, the main app, and this is just Docker container that's deployed to AWS ECS. And we can also check out the stack, the app stack. So it's just basically a Fargate service that is deployed to ECS via this CDK construct. That's application load balanced Fargate service. And you can modify it to use your own domain, your own certificates, whatever you want to utilize in your application. And this Streamlit application is defined mainly in the app.py, and the agent components are defined in the subfolder. So here we are constructing the visual interface for the user to interact with. And then in the agent class, we are actually communicating with the Boto3 SDK, and this will allow us to talk to the agent. So here we are talking to the agent and sending the prompts, and then we are also looking into the responses. And a lot of this real-time trace output that you see in the demo is defined here in the handlers, where we are actually looking into the different types of traces that we receive, and from these traces we are then displaying them with Streamlit. So Streamlit is a very convenient way, if you're not a front-end developer, just to develop everything in Python that you're used to, and to have something up and running that you can show to the user. So if I would like to run the Streamlit now locally, I can just execute this run command and open it in my browser. And then I'm seeing the whole application, and I can just ask the application some questions, the agent some questions. And for example, here, this tools example, I will just fire it up, and it will invoke the agent, the supervisor agent. It will give me the traces back from the Bedrock SDK call and render them here in real time for me. And what is also happening behind the scenes is that we are sending this information to LangFuse. So you added your LangFuse API key, and that allows you to collect all the information that the user is seeing on the front and also on the back end. So now, for example, for this input query, we are saving the output. We are doing a calculation of the costs based on the token usage for Claude. And we are also saving all these sub-events here, like single model invocations, reasoning steps as metadata. So whenever a user would rate this example as not very good, which is possible here with the thumbs up, thumbs down. You can also add a text if you want in the future. Then this feedback will be attached to the trace. And for example, here I was giving a positive feedback, and in this way you would be able to identify prompts that led to an incorrect answer, and you will be able to debug where it went wrong and improve your orchestration and improve your instructions to better handle the failing scenarios. and you can always add those traces to a data set. So for end-to-end testing, this would be convenient, and then you can always test your latest agent deployment against those labeled data sets. But that's a topic for another session. Evaluation is very complex, and this blueprint is just the starting point to get you up and running.